Good afternoon everyone, welcome to the channel. In today's video I want to talk about transfer learning again. This will be the second video about transfer learning, and today I want to discuss about VGG16, which is another state of the art model, and I want to use this model to classify SVHN dataset images. SVHN is a street house number, some kind of dataset. So without talking too much, let's write coding. Okay, so as usual, first I want to import the required libraries. PyTorch, from torch import in and optim. Now let's import torch vision. So we want to check the version of torch vision. From torch vision, import datasets, models, transforms. From torch info, import summary. From import numpy, matplotlib. Okay, so these will be our required libraries. So our PyTorch version is 2.0.0, torch vision is 0.15.1. Now let's define the device. Torch coda get device name, new line, device will be coda if torch coda is available, else it will be CPU. So print device is device, finally total number of GPUs. Torch quota device count. So this is our GPU NVIDIA RTX A5000 and total number of GPUs is 1. Okay, now number 3, apply transformation. So transform will be transforms dot compose, transforms dot resize, so 224 by 224. This will be the resized image size. Transforms dot to tensor, transforms dot normalize, mean will be 0.485, 0.456, standard deviation will be 0.229, 224, 0.225. Okay, now let's see how we have selected these particular values. So weights models dot VGG16 weights dot default weights transforms Okay, you can see these are the values that we selected in this. Okay, now it's time to load SVHN dataset. This will be 4. So train datasets dot SVHN. So root data SRC split train download true, transform will be this transform. Okay, we have to do the same for test dataset as well. So split test. Okay, I guess that's okay. Oh, sorry, datasets. Datas. I think it's okay. Okay, so our dataset is now being downloaded. Let's wait for a few seconds for the download to be completed. train dataset has been downloaded. Now test is downloading. Okay, so download is finished. Now let's check a few things. So length of the train dataset. Boolean train dataset. So length of the test. This will be test. So 73,256 trained samples, 26,032 test samples. You can also check the shape. So shape of the train dataset. So in that case, shape. So and copy test dataset. So these are color images. That's a 32 by 32 pixels. Now let's see train dataset dot targets train dataset dot labels. Okay, let's check the what type of labels we have available. So there are 10 levels: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's visualize few images from the training samples. So it's figure 1 plt dot figure fig size 1812 for image 1 in range. Let's check images within this particular range. So fig1 dot add subplot. So 5 is rows, 8 is columns. We have to mention the position. Okay. Now plt dot I'm show toss clamp train dataset image 1 0 dot permute on to 0. So we have to put these channels at the last position, otherwise this I am sure will not work. So this will be 32 32 3 for this one instead of 3 32 32. Okay. We have to mention mean 0, max 1. plt dot train dataset image 1. This will be 1 for the label. Let's make the font size 15. plt axis off, and we have to increment by 1. So this is some of the images from the training samples. I'm not sure how I I can see 1 and 6 here, but why this is 1 and also 1 and 6, why this is 6? I cannot understand these two at all. Okay, so we have some house number dataset. Very weird. So many 2s here. I can see partially 9 here and 8 also, but it is labeled as 8. Okay, now let's do the same for the test. So this will be test. Just change this. Test dataset. This will be 2. What's happening? Oh, sorry. Oh, now it's okay. Again, same situation. I have no idea why so many digits but only 5. Okay. Now let's okay, 4. Now let's 5. Define data loaders. Train data loader. So data loader will convert the dataset into an iterable, which can be used for training the neural network model. Okay. Shuffle true. Same for the test case as well. So test shuffle false. Test as well. Let's check the length of the train data loader. Same for the test. So the length of the train is 2290 and test is 814. And apart from the last one, I think everything has 32 images. Okay, now the pre-trained network, we will use VGG16. There are few variants of this VGG architecture. You want to use the 16. So VGG16 models.vgg. So there are 11, 13, 16, 19. So let's use 16 for this video. Pre-trained true. Okay, now let's visualize the pre-trained model VGG16. Okay, so create an instance and send it to GPU. Then torch info summary, model input size, so this is batch size, number of channels, and since we have transformed it to, so we have resized our this special dimension to 224 by 224, and this is the minimum size required as for input of this model. So let's visualize it. Okay, so there are significant amount of layers. So these I guess are the feature extraction part, then adaptive everything, and this is the classification part. And if you check this part, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 layers with tunable hyperparameters, tunable parameters. So that's why this is called VGG16. Now this is for Imagenet. We can see 1000 finally, but we have to change few layers for SVHN dataset. So now modified pre-trained network, architecture for SVHN images. So modified VGG16 models dot VGG16 pre-trained will be true for paramean modify 16 parameters. Param dot recurse grad false. We're gonna use the trained weights and biases. We do not have to optimize the parameters again, but we need to change few things for making it suitable to use for SVHN images. So let's change this part first. So currently it is 77. We want to reduce it a little bit more. So nn dot adaptive FG pool output size, instead of 77 let's choose 22. Then dot classifier and dot sequential. Okay, so linear and dot linear. In features 2048, out features will be, let's say, 1024. Then add a reload svhn dot true. Add dropout. Okay, let's copy and change. So this will be 2. So now this in feature will match the previous out feature on 2024. Let's make it 512. And finally, do not need this to 512 to 10. So we have 10 classes, as we have seen, 10 classes. That's why this is 10. Oh, sorry, I have to change this one as well. Now let's visualize. Visualize the modified pretrained model. Modified architecture. So let's create another instance, modified model. Send it to GPU. Again, torch input summary. Same as before. So you can see we have changed these layers. Okay. And another thing I need to mention, so why this is 2048. So we can see 512 to 2, the output of adaptive UVG pool 2D. So if we multiply 500 to 2, this becomes 2048. That's why this linear layer takes the input features of this size. Okay. Now it's time to define the train batch. Def 10 train batch, data labels, send data to the GPU, labels to GPU as well. Model data, criterion, output labels, optimizer, zero grad, loss backward, and optimizer. step. Return loss. Now define the test batch. Inference mode. Model and criterion. .ifl. Let's copy this few lines. Return loss. Define the accuracy function. Okay, again proceed. We do not need this line. Pred labels. We do not need pred values here. We'll use it later. So output dot max. Correct labels and return correct dot CPU detach numpy, converting tensor to numpy array and then further converting it to a list. Okay, now set up model so modified criterion, also known as loss function, and optimizer. So model to train, criterion optimizer. We'll use SGD for this problem. Previously we used Adam for ILSVRC, I guess. Parameters. And learning rate, let's use 0.01. Now it's time to train the model. So np dot random dot seed. N epochs 15, train loss, test loss, create to empty list, train accuracy test, accuracy, for epoch in range, same as Imagenet. Test accuracies, for data labels, train data loader, train batch loss, train batch, data labels, model to train, criterion, optimizer. Then we want to append per batch loss to this list. So trn batch loss item, accuracy function, data labels, model to train, accuracies, train accuracies dot extend turn batch correct, np dot array train losses mean, train accuracies, so we have to do the same thing for test case as well. We do not need optimizer for test batch. Now train loss dot append train per epoch loss, train accuracy append this is small test per epoch loss per epoch accuracy, again accuracy accuracies, okay, print epoch train loss train let's copy this line. So this will be test per loss finally let's see if it works or not. Okay, the training is working, so we have written this particular cell block correctly. It will take a lot of time, although the number of epochs is only 15. So I will join again when the training is finished. Welcome back everyone. So the training is finally finished. I didn't exactly count how much time it required, but it definitely took more than 1 hour just for 15 epochs. So now I want to calculate few other things. So we have to, after training, we have to plot model loss and accuracy. So epochs in p.h 15 plus 1 plt dot figure size epochs train loss red also the test loss number of epochs font size will be 20 plt dot legend. So we have to do the same thing for accuracy as well. This will be 2. This will be test accuracy. Accuracy. This will be accuracy curve. This will be accuracies. Hope it's okay. Or let's put a semicolon. So this is our loss curve after 15 epochs, both decreasing, and this is accuracy curve after 15 epochs increasing. Obviously train accuracy is higher than test accuracy. So finally we have to perform the model prediction 16. Okay, let's create a few empty lists. Samples, props, labels for AB, output f dot softmax model, retrieve the model from GPU to CPU, provide the samples, append the probabilities, float, then labels, append, add labels. Fig axis, plt dot subplots, 3 rows 3 columns, fig size will be 1715, I is equal to 0 for r in range, r is for row, for c in range, c is column, rc dot I'm show dot clamp samples I 0, set title, font size 20, set color to black. So these are our actual labels. Samples, labels I 20, set color to blue. These are correctly predicted labels. If this is not the case, then we want to change it to red. These are wrongly. And set Y level. This will be threads. So probability of the probability of the predicted class, it will not be correct in each instance. So rotation 0, label pred 30, and set color to magenta. So this is probability of predicted class. Empty the x-tick values, empty the y-tick values, increment I by 1. Something is wrong. Threads is not defined. Oh, sorry, probes, not threads. Something. Sorry, label pad, not bread. So many typing mistakes. Okay, so finally, so black is actual level. So actual level 0, predicted 0, 1, 1. This is actual level 3, but I cannot understand it very well. Predicted 9. Then this is actual 2, predicted 2, actual 5, predicted 5, 4, 4, 1, 1, 4, 4. So in this 9 images from 21 to 29, so we got one wrong prediction, but after 15 epochs we only got accuracy, train accuracy 86, test accuracy 77. For saving time I only trained for 15 epochs, but if you have time you can train for 30 epochs or 50 epochs to see whether it becomes better or worse. So this is how we can classify street view house numbers dataset, and these values are predicted probability of each class. And since we use softmax, they are in the range of 0 to 1. So this is very high. All these values are high. This is low, but also predicted correctly, and this is not as high as predicted wrongly. Okay, so this video has become very long. I do not want to prolong it further, so that's the end of this video. Thanks for watching.